Okay, so thanks to all of you. Let me introduce myself. So I'm Todd Falcou. I'm an associate professor from University of Paris and also CTO of Numscale, which is a company that deals with high-performance computing. And I will speak for quite a long time about a subject that is probably both the most obscure and most, intriguing concept in C++, which is expression templates. So the original talk title was expression template, who, when, what, where, how. But I decided that speaking for 5 hours was too long, so I just shortened it to 3. So it's more like past, present, futures for some definition of past and present. So what we will be doing in these ongoing sessions is try to actually grasp what are expression templates, both technically, how it should be written and how it works, and why you should care or not, because sometimes you just don't need them, okay? And as all tools, it's also important to know when you should not using it, okay? So the presentation workshop tutorial is basically split into 3 sessions. The first session will be very introductive, starting from the ground up, writing everything by hand, see where the problems are, what the main concepts, and where the difficulty starts to pop up. And then on the second session, we will speak about some tools which are already there for simplifying that, mostly Boost.PROTO. I will try to get as much as I can out of Boost.PROTO introduction in 1 hour. If you really want to dig into more details, I have another presentation on exactly this for a bit longer time, that which are available on the CPP Now video websites. And the third part will be about how can the new way of actually programming using C++ 14 and beyond actually simplify the simplified version of expression templates, and how we can use a new paradigm of C++ 14 to actually solve the remaining issues that we will go over. So it was advertised as a workshop, but as a setup, it's not really very cool for typing code for a long time. So what I will do is we will have a bunch of slides where I try to explain stuff, and more interactive session where I will be probably writing code live and asking you questions and see how we should be doing things. Everything is available on GitHub. Okay, I don't know if it's zoom enough. Okay. So you got the slides and all the example codes that you will be seeing now. It's maybe changed a bit afterwards, but all the material is there, so you can just clone the repo or download the files, and everything is inside. I will also use my text editor and an online compiler, so we can actually get the example running. Okay. So first things first, let's make a small poll. How many people out there actually know what expression template is about? Okay, not bad. And if you know what it's about, how many of you survived? Okay. well, that's a classical joke we get about expression templates. It's so complicated you basically burn your brain out. But we will try to demystify that. So, what is expression template? What's the goal? So for a long time, designing libraries in C++ was all about getting a correct model, probably a correct object-oriented model if you were into this, and try to make the library API fit this model and fit into the actual, let's say, historical C++ language syntax. And after a while, what we found out is that it's quite limiting. And we borrowed the page to other languages. I would go over that. And now, one of the trending stuff is writing a library as if it was providing the services as another language. And by designing a library as a language, with all it means, we will see that we can actually extract more optimization opportunities, and the YOL code will become more clear for the end users, because they will just have to write whatever they want to be doing instead of writing what they should be doing to get the effects they want. So we end up with code like this. Okay, so that's something I picked up from Keiko's here, GitHub, which is a reimplementation of LLVM kaleidoscope using Boost Spirit. So Boost Spirit is a library which is in Boost that provides a way to define parsers and text generators. And the main asset of this library is that you can actually write something that just happened to look like you just copy-pasted a piece of grammar, okay, over there, directly into your C++ code. Okay, so you just write what you want to be doing. You write what you want to achieve. And the library itself returns your description of the problem into the actual optimized and strictly minimal code to do this. So it looks like everything but C++. Okay, the only stuff that looks like C++ is basically the operators and how the code is set up. But if you look at this part between identifiers and program, well, it doesn't look like regular C++. And so the deal is, by having a way to shape the language the way we want, this way for Spirit. How many of you have heard of Eigen? Yeah, so Eigen use the same techniques, okay? We have a parallel programming library called Boost SIMD, which uses the same stuff. You have Boost MSM that use same kind of mechanics to help you write a state machine directly as you will be writing in a UML document, and so on and so on. So we push into those libraries domain-specific information, and the library uses this to get whatever they need to choose what kind of code they should be generating. And so the question is, how does it work? So the main issues is to look at this on a different angle. So actually, if you look at what's going on, expression templates is actually pretty old. The main idea is to say, I want to write code that looks like something else, captures the meaning of what is being written, doesn't do any computation, and ship some kind of complex temporary object somewhere else. And the somewhere else we take care about looking at the whole pictures and decide what to do. And the problem is, up to recently, and still now, the language itself was not very keen to help us writing this in a comprehensible manner. So expression templates as a techniques, as an implementation techniques, has been not very something that people accept as normal, okay? Its support is very flaky. Some people actually argue about the fact that we should not be doing this and that's the job of the compilers or so on and so on. And now, with the advent of move semantics and air value references, copy allegiance, the main issues about we should be using expression templates to do those meaningful expression construction for performance reason is actually put in question, because if we have all this core language support, why do we need this? So the idea of this is to actually see what we can do with that and try to find a way to make it work properly. So why using expression templates? So you have different reasons to do that. Answer A, performances, okay? One of the selling point of expression template, we will see that just after that, I dig up some old emails from the 90s, was to prevent creation of temporary array object on the stack while composing large algebraic-like expressions. So by removing the need of temporaries, we were making less memory allocation and the code was more tight. So answer B for code clarity, because writing what you want to do instead of what you should be doing is easier for the writer first and for the reader afterwards. Okay. And C, just for bragging rights, because man, that's one fine piece of C++ code I just wrote, and I'm pretty proud of it. And of course, answer D, all of the above. Okay, so we will go over all of this, probably not C, but mainly A and B, okay? A bit of C, actually. And we will try to see how everything fits, okay? So, yeah, as I say, we will explain how everything works. We will actually show that it's not that complicated. It's not complicated, it's a bit complex. Every sub-pieces we will be using to build our small handwritten expression template engine is in itself a very simple idiom that you will probably use elsewhere already. The complexity comes from the stacking of all of this in a very tight space. Next part, as I said, we will see how we can actually generalize that in Boost.PROTO and see how the new C++ can actually be useful. And we will discuss some new stuff and how we can actually make all those techniques something that the language can provide us. That's more or less what we will be doing. So first part is, okay, basic principle, how everything is supposed to work, okay? So first is, okay, where does it come from? It's actually a very, very, very old technique, 20 years old, as I say. So it's actually a joint discovery by, on one side, Todd Veldhuizen, and on the other side, David Veldhuizen, around 1994, 1995. So Todd was an intern at Rogue Web Oregon, working on the image processing libraries dealing with image algebra, you know, like sum of images and scaling of the pixels, and so on and so on. And he discovered what will become the expression template techniques by trying exactly to do what I said earlier, is trying to optimize all those temporaries objects. Rogue Web issued a technical report on this. I think it was 94, and there is a whole bunch of C++ report articles that you can find on the internet about explaining all the intricacies of what Todd found. So, and at the same time, David Veldhuizen was working on some value array implementation and just end up doing the same exact kind of things. And it was actually proposed on somewhere. And the funny thing is that the actual first users of this that pushed the technique into the public was a physicist that actually published a paper in a journal called Computers in Physics that say, hey, look at that. We can actually now write C++ code, and it's as fast as our old good old Fortran, which at the time was big. So I dig up those. Okay, so that's the first email actually speaking about the problem. One of the first email, I guess. I couldn't go, earlier than that. So it's a mail by someone that made the matrices for complex number, and the question is, I have a temporary that should not be there. How can I actually get rid of that? To which David, the other one, say, okay, you can. It's a bit complicated, and start the biggest understatement of the century. It makes heavy use of class and function templates, okay, to avoid the generation of temporary. So that's probably the first trace that's coming from CPP, comp CPP something on Usenet. Okay, so that's the first stuff I found about this. So yeah, heavy use of function templates. That's small to say. So it's old, doesn't mean it's not useful yet. So how does it work? The main issue when you want to understand what expression templates is actually doing is to actually look at what a compiler is doing. So let's say you have this kind of arithmetic expression going on, okay, with parents and operators, identifiers, constant. So when you pass it with your brain, it's clear what's going on. But for a machine, it's a bit more complicated. So as a compiler, what you want to do is understand what this expression means and what are its components, so you can take decision about what to do with each of them. So one classical way to do that, probably the only sane way to do that, is to build what we call a derivation tree or syntax tree, which is a tree representing the structure of the expression in a way that we can reconstruct it by traversing the tree. So it goes like this. So that's the full-blown syntax tree where everything is set up, okay? So this EPA, so pardon my French, it's expression purement algébrique, pure algebraic expression, is made of something on the left, an operator, and something on the right. And this something on the left or on the right can be either another expression of arithmetic components, okay? Or, if we look down the tree, an identifier, x, y, z, or a constant, 3 and 4. And by combining this, you can build arbitrary large expression with plus, times, constant identifiers. So, if we wanted to store the structure of this tree somewhere, we will probably end up having some kind of tree structure containing the left child, the right child, and whatever happens when you traverse the tree, okay, the operator. So you can actually write regular, runtime-based, virtual function call-based implementation of these three classes. You'll probably end up with a tree base class with that all the interface you need, and you will probably have subclasses like constant, identifier, and so on, binary expression, that will just do whatever the name implies, and you can put into a vector or another construct of base expression pointers or reference. So you can actually write this and have it run at runtime, probably using some kind of factory. But if you look at the problem is, you have two stuff going on. You have something which is intrinsically dynamic or known at runtime, the value of x, y, z. You doesn't know them yet. You know it's a value behind this identifier, but doesn't know what it is. And there is another part which is completely known at compile time. It's the static structure of which piece of tree goes where. The fact that you have a tree with a minus operators containing two subtrees, one with a times operator and one with another minus with a constant on the right and a plus on the left, is completely known as compile time. You doesn't need to store this information at runtime, okay? So the trick is to find a way to say, okay, what I want to have is a representation of a tree with some amount of children that can embed these structures in a compile time way, which means in a type, okay? So the idea is to say, okay, that's pretty trivial. I could just have a first type. Oh, sorry, I'm going over myself. So that's the full syntax tree. And so what we will be doing to do is, once we have those types, okay, we can do something like this. We start from an arbitrary statement using our library on the left, yes, on the left. And on the right, we see another kind of tree, okay, this blue and red stuff, okay. And if you look at this tree, it's far more simpler than this one, okay, because we stripped it of all the syntactic information that didn't bring anything on the table. We just have a simple tree, which is a succession of operation node and subtrees. And subtrees can be a constant or something else, but everything about the actual syntax, the actual parents or whatever is stripped. That's what we call an abstract syntax tree, okay? That's just boiled down version of what the compiler is supposed to generate. And what we do, if you look closely at the color code, is we embed in red the structure of the tree into this expression type in the big box on the left. And if you go down this very complex type of expr of assign, expr of matrix, expr of plus, of course, of multiplies, if you go down this in one way or another, you are able to reconstruct the tree because you have all the information. I'm making an assignment between something, which is a matrix, on the left, with something which is an expression doing some plus operation with left-hand side and the right-hand side, each of them being something else, which can recursively be another expression. And this information will be stored into a type. And the object you build actually store value, copies actually, or reference to the runtime information into the leaf of the tree, the blue box, okay, which we call terminals. And what we will be doing is, once we did this capture somehow, you can actually take the type of this massive tree and you can torture it as much as you want using template metaprogramming, because that's a type, so I can transform it the way I want, until you end up with something which is exactly what we need to take decision about what kind of code do I want to generate. And in this example, what we do is say, okay, we are dealing with matrices. I have my trees that give me whatever operation I should be doing on every element of my matrices. So I will just pull out a loop nest, and because I feel it, I will just put an OpenMP parallelization pragma on it, and I will just replay my tree, my assignment between x and cos of a plus b times a, for every element of the matrices inside this box. Okay? So I wrote that, and the compiler did this for me, okay? And the trick happens there. We transform this IST as much as we want until we know what we will be doing, okay? So that's the first stuff we will be needing to do. We need to store the matrix, we need to store the expression as we build them. First challenge. Second challenge, we need to find a way so that construction is easy and hidden behind operators and function overloading. And third, we need to have a way to traverse this tree, to transform it, or to evaluate some value out of it. And when we know how to do those three pieces, we can actually generate whatever we want, okay? So we take an expression, and we do something which is very kind to what a compiler is doing. We extract this tree of it and try to reason about this tree. The cool thing with tree is that we can actually do a lot of stuff with them, okay? Because the natural process of tree is based on recursions. We will probably have pattern matching on what kind of node I am traversing at the moment. And we can just write regular, simple code that we just visit this tree and take decisions about it. Okay? Is it clear? That's the main idea of what we'll be doing. Just build the tree and go down it or up, whatever we need to do. And when we traverse it, we just decide what we do with it. Okay? So, well, what do we need? We need to store the expression, as I say. And actually, we need two stuff. Storing the operation I will be doing at crossing the node, or not the operation, but actually a representation of what's going on. Okay? We need to store the sub-expressions. And the first question would be, should we be storing them by value or by reference? We will see that this is actually a real problem. And we need a way to traverse them to do something, as I say. And then how do we capture the expression? We will just be using operators and function overloads. And it's a great tradition of writing efficient C++ code. We will just write functions that do nothing, except returning a representation of the small trees that are currently building. So basically, your plus function won't do anything. It just returns an empty shell that says, yeah, I just crossed a plus operation between this and that. This is the information I found about them. Continue with the rest of the expression. Okay? So, let's have a look. Let's start with something very simple. Okay? We have an unary expression, which is an expression, an operator, or functions that take exactly one argument. So, could be like unary minus, negation, absolute value, whatever. And the whatever operation that's being done when you traverse the tree is stored in the type called tag over there. So this will give me whatever happens when I'm encountering this expression. And as I say, I have only one argument, so I will have only one child, which is another subtree. And of course, this tree could be of any type. So as I don't know what it will be, I will just, again, store it as a template parameter there. And you can actually build an unary expression by taking some child and put it inside it. And for the example, what we do is we give this expression a function call operator that will just evaluate the value stored into the expression. Okay? And what do we do? Well, the tag actually is a type which is itself a callable object. And so what we do is I evaluate my child, okay, C parents, and whatever this gives me, I pass it to my operation. Okay, and I return whatever this operation does. So if you build an unary expression of unary minus something, you will evaluate the something and return minus this something. Okay. And obviously, I just did the simple version so it fits on the slide. Obviously, you can actually no except and const expr whatever you want in this. Doesn't change anything. Okay. So that's the unary expression. And in a very, very, very complex way, this is a binary expression, which is basically the same, except they have two children. Okay, P0, P1, get stored, store the operation, and then when you evaluate the tree, you just call the operation function on whatever the result of the evaluation of the both children is. I could have written a ternary expression or whatever, same things. If you crush your brain a bit, you can actually write just an expression that takes a class ... childs with children, sorry, with an arbitrary number of children. It's a bit more complex, but you can actually do this. So, okay, I store unary expression in something like this. Okay, I store binary expression in something like that, right? Okay, and of course, if you buy the binary expression of binary expression and so on, you will just store them one into the others. Okay, the type give you the tree structures, and the value give you every value around the tree when you go down. Well, we have a special cases that we call terminal, which is also the leaf of the tree that contains a value or something that will contain a value. It's usually simpler because you just need to know the value you store inside it. Okay, that's a very simple terminal. We will see later that it's actually a bit limited, but for the example, it's perfect. So I'm just constructing a terminal with a value it's supposed to contain, and whenever you ask me to evaluate myself, I will just return the value to you. So a terminal of float containing 3.5, when you evaluate it, just return you the floating point 3.5. And if you had a unary expression containing a terminal, when you will evaluate the expression, you will grab the terminal value, pass it to the operation, return the value of this operation. And everything is just done recursively by this chain of operator function calls, one into the others, driven by the number of parameters of each expression, and whatever happens when you call the operation function call. Okay? So basically, if I wanted to make a bad joke, we are done. Thanks for coming. Okay? It's a bit more complex than that. Okay? But you see, the magic is there. We have this recursive call of evaluate myself, please, that go down the tree, go down the tree. And of course, depending on what you want to do, this is a simple direct evaluation, but you could actually have all the option of tree traversals, infix, prefix, postfix, whatever. You could actually also have an operation that just say, my result, well, it's a new tree that I built from whatever I got inside. Okay? So this is where the magic lies. These recursive calls. And the fact that you know in each operator what you are doing, because you know that you have a tag and so much child. And the terminal just returns the value. Okay? Well. But okay, now what I want to do is actually, I don't want to construct those expressions by myself, because it's completely not expressive. What I need to do is find a way to have operators, like operator plus of something something, and you end up with a binary expression of plus something something. So you can just call plus, and you get your expression built. Okay, that's what we want. Except we basically have 3 different types there. Okay, and all of these 3 types can actually be used on the left or the right-hand side of our plus operator. Okay, so the question is, how can I write this operator so it does not end up as template A, template B, operator plus of A, B, which is far, far, far too much unconstrained. So the idea is to find a way to say, I will take everything there and put it into a common box. And I will try to apply my operators on this common box. Okay, so that's basically what we will be doing if we were writing a runtime-based polymorphism versions. But we don't want to do this. So what we'll be doing is using a very, very well-known idiom, which is a curiously recursive template pattern. Okay, that's quite a mouthful. So apparently it's a pattern which is based on some kind of recursive template which act in a curious way. Okay, so let's have a look. So the idea is, how can I simulate runtime polymorphisms at compile time? Well, you write some things that look like this. Just have a look at that. How many people know about the CRTP? Just another poll. Yes, cool. So I probably won't spend too much time on that, but for the others, here's what goes. You have a base class, which is parameterized by the template types. And you provide an interface. Okay, and you have a derived class, okay, that iterates from base using its own type as the template parameters of the base class. So derived iterates from base derived, and as strange as it looks, it just works. And what happens in base then, in the interface function, you can actually take this, cast it to whatever its template parameter is, and call whatever function on that. And why does it work? Why does it work? It works because whatever base of t you have, by definition, it cannot be anything else but a t. Okay? That's a bit crooked. Okay? And actually, I think this is more crooked than the your other part of the expression template system, but whatever. It's a bit crooked, but it works. If you have a base of t, you cannot be anything else but a t by construction. So casting yourself into a t reference works. Okay? And it could be a static cast. You don't even have to do dynamic cast because you know you are a t. So we just go down. It's basically, I think we can say some kind of programmatically done slicing of object. I think that's the best image we can have of that. We just slice base up to the t. No, actually, it's not the slicing. It's the other way around. We actually pull up your base into a t, a full t, and you do whatever you need. So what do we win with that? The interface function is inherited by every type inheriting from base of something. So we have a place where we have a common interface and we know what to do with it. And the actual implementation is stored into the subclasses, like with regular polymorphism. So we can hide the type-specific implementation into the base, into the subclasses, and we can take a base of something and call whatever we want on it, and it will be dispatched to the correct version. So if we take that and put it on our unary and binary expression and terminal, we end up with this, which is not very readable from far. Okay, so let's have a look at how it looks a bit bigger. Okay, it's probably better if I show you it there. Okay, is it okay for the size for everybody, or should I zoom a bit more? Or it's okay. Okay, so we have these base expr classes, which is basically our base root for our CRTP system. We just hide the static class inside the self function. That's something which is very classic. And what is the interface of our expression? Whatever the type of expression, unary, binary, terminal operation, we want to have these function call operators. So we ship it into the base class. And what does it do? It takes self and apply its call operator. I could actually have called this another function and put it into a private section, but that's details. So what happened for unary expr? Unary expr inherit from base x of itself. Okay, same constructor, and the actual implementation of the function call operator, just as before. We just inherit from base expr. Okay. Binary expr, same stuff. We inherit from the base expr something. Okay. Same for terminal. Okay. And now we go to the actual meat of the systems. I want to define my operator plus. Okay.
Could you go back to the top?
I can do this. So base expr, it has this self member functions that just do, it just writes the static stuff. Okay, and then you call it inside the whatever interface you want. Yes, Luis?
So since this operator grant in base expr has the same name in unary.
Yeah, it just occurs to me right now. It just, I should have been calling it something else into the base classes. Yeah. But we never actually endorse the non-base expr. I will go to that afterwards. Okay? But yeah, it should have been a better style. I will correct it on the GitHub. It should have been a better style to have different name. Because in this case, you are not very sure you don't mask anything. Well, the fact is that in these systems, that means that if you end up actually dealing directly with an unary expr and you call the whatever, you directly go to the whatever. You don't go through the base one and do the cast. And when you go through the base, you go through all the oops and go back to the correct one. Okay? So we have this self stuff that used to cast yourself into one of your subclasses, and you ask your subclasses to take care of the actual processing. Okay? Any other question? Okay. So from there, it's just boilerplates. We do this for every kind of expression. Very repetitive work. Don't really want to do that at home, really. Same for binary, same for terminal. And let's have a look at operator plus. We will go on the other stuff afterwards. Look at that. This part, lines 56 to 60, this block. So what we say is that when we call operator plus on two different base expr of whatever, what I do is I build a new binary expr, the operation being plus. Okay, so that's this plus underscore is telling us. What do we store? Whatever is inside the base expr. Okay. And we just build the object storing the things. Okay. And for the repetitions, we do the same for operator times. Okay. Same things, different tag, same system. Extract the self from the base expression, store it into a new block, ship the block. So we didn't do any computations there. We just built a very lightweight representation of I just came across a plus into this expression. So I would just want to inform you that I just did this. And you will take care of that later. And what do we do in plus? So plus can be an empty type, just a tag. But what we want to do is actually use it as a callable object. So what we do is we just give him a polymorphic template operators function call that take a t a u and just return t plus u and whatever the type of this is. And same for times, we just do t times u. Okay. So that gives us the operation call syntax for the operation inside the expression. Okay. That's the classical way to do it. So what happens now when I call my parents operator on a binary expression, let's go there, this function there, which sit inside tag, okay, this operation is actually this piece of code. And when you go down inside the tag operation, you don't care about the fact that you got a binary expression and something and something. You just get raw values as an input, and you do whatever you want with them. Okay? Because we evaluated whatever before, and what we have is recursive evaluation of all of this. Okay? So I have a way to build those operators, right? Okay? And I can write stuff like this. Look into the main. I just build a terminal of int containing 4. And I build an expression which is d plus d. I store that into e. And I just ask for the value of e by calling this evaluation operation. Okay? Well, still not very fancy, but let's see if it actually works and compiles. Well, I'm a bit lazy, so I will just ask this guy to do all the work for me. So, base expr, unary expr, terminal, binary expression, plus times. So I don't remember what I do. So 4 plus 4 probably give us an 8, which is probably the most convoluted version of printing 8 on the screen you can actually find. Well, I can do worse than that, but that's currently probably still too much. Well, just joking. So what happens if I just want to do this instead? Well, I can just write it, okay? Pick, compile, link, run, thing. 20, is it right? Yes. 4 times 4 plus 4. What? Oh, crap. Because I guess it's too... Okay, so ad hoc solution. Is it better? It's actually simpler than me trying to fix my ratio on the screen, so sorry for that. So, okay. So, if you look at the compilation line, I'm using C++14, but just because I'm a lazy guy and I put auto everywhere. Okay, of course, it's not needed. Of course, it's not needed, but you can, if you want, you can try to write this not using auto, and I will probably get an appointment with you next month, okay? Because, as you can see, already this auto there to be replaced is not that funky, okay? I have a t and a u, and I want the type of arbitrary t plus arbitrary u. In C++ 98, that's not that quite easy. Yes, questions?
Just to make sure I'm understanding it, if we were to expand that type, it would be the ASCII that we were looking at for that expression?
Yes. What I will do just now is I will try to print the actual types of E, okay? So, beware. Oh, yeah, where? Maybe they have what I need. Let's pray. Yes, they have it. So, okay, so let's have a look at the tip of everybody there, D and E, okay? So what is the, how does it work already? Yes, Boost the mangle. Yeah, it's probably this. So let's take the type ID of the whole thing and ask Boost the mangle to print it into a readable format, okay? So what happens? What is the type of D? We expect it to be something like struct terminal of int. If not, something is rotten into the kingdom of Denmark. Okay, it's not a member of Boost. What the crap is that? Who's in charge? Okay, actually it's not me, so well, just 5 seconds. I don't remember where was the damn thing is. core. Yeah, you know, reading the doc is for the weak, you know. Core, mango, where is it actually sitting in? Oh, Boost core, of course, I'm stupid. Should have known. Okay. It's terminal of in, right. So now let's have a look at what happens if we do this. So what we expect is something close to unary expert plus terminal in, okay? Let's have a look. Binary expert plus terminal in. Okay? So question, why don't we just store binary expert of plus base expert terminal in, base expert terminal in? Why don't we just do that? Why am I supposed to extract the self from the base expert before storing them? What? Yep.
Well, you might want to add some more data to your.
Yes. Yeah, exactly. You may want to carry on more data than just the base expert allow you to. Okay. You may have special members or special data set into your actual derived class that you really want to have when you store them. Okay. So that's d plus d. So let's go to the next level. D plus d times d. And we will touch the first issues. Okay? Well, that's exactly what we think it should be. Okay? One more time. Starts to be big. Okay? Okay. So first problem. Look at this frigging symbol size. Okay? First one is okay, second one is okay, the third one starts to be, you know, worrying, and the last one is completely out of control. So, well, just so, and of course, you don't really want to go into these kind of territories, which actually happened. Okay, how many frigging parents do I have there? Okay, that's cool. Yeah. So I was about to make a joke about the compile time, and then I remember that the latency there is probably more the network than the actual compilation. So, yeah, it's still worrying. Let's blame the Wi-Fi. Okay. Come on. Okay, while it compiles. So yeah, first issue is this very long symbol name. Doesn't sound like much. I mean, just symbol name. But at some point, the compilers has to build it, to store it somewhere in more or less some kind of, still compiling. Come on, okay. It has to store this symbol name into something which is probably a string-like structure, which probably means that the compiler is allocating memory to store it, okay? And it's still compiling. Okay, well, meanwhile. So, symbol names, that's the first issue we will meet. That's 99, well, okay. That's maybe 75% of why expression templates are said to be slow to compile. But that's outrageous there. Okay, symbol names. Symbol names mean strings. Longer strings means more complex. Oh, let's say not more complex, but you require more memory, and more memory means maybe more swapping or whatever, and your memory consumption of your compiler will just go up, and at some point, that will be the main issues about that. That's really worrying, actually. Okay. Okay. Let's blame. Okay. Okay. I think it's yeah. Okay. Binary f expert of plus between what? Between times and plus and times and times and plus and plus and times again and times again and done. Okay. That's quite a mouthful. Okay. So that first limitation, and of course, if you think about it. I mean, it's just, as much as your tree is deep, it will go worse and worse, okay? But it's exactly what we think it should be, okay? No surprise there. And of course, the important thing is, okay, but I will just cut on that, because I don't really want to spend 1 more hour waiting for the compilation. Of course, the important thing is when you do this, okay, you end up with the int you asked for. Okay. So this place where you go from the tree form to the actual evaluation of the tree, it's sometimes called what we call a compression point. It's a point into the expression template system where you stop being lazy and you do some work. And there we put it there, just on this operand part of parents, but we can actually put it wherever we want. Okay? So let's have a look at something else, a different version of this. Okay, this is this one. Yeah, this one. Same idea. Okay, same basic code. I just change the small stuff. Look at line 85. I can write u equals d times d plus d times d. Okay. I don't even call parents anymore. I just use the assignment operators. Of course, what happens? Let's look at terminal. Because what u is, it's a terminal float. So what this assignment operators of terminal does, it is, we take a base expr of whatever, and we say, cool, we have a base expr. I know it's some value behind it if I evaluate it. So I will just evaluate it and store it into my value. So we move the evaluation from let's just evaluate it to a more, let's say, semantic-driven evaluation point, which is whenever I assign a random expression to a terminal, I want the expression to be, condensed, evaluated into the value, and I store it into my terminal. That's the classic things. Assignment operators do the compression point. That's what all linear algebra expression template-based library does. When you write my matrix equals this huge amount of matrix operation, the assignment operator of your matrix class will just do some loops, and for every point into my matrices, I will store the evaluation of your expression on the right for every point I'm currently computing. So you can put your compression point wherever you want. And by wherever you want, it actually means wherever it makes sense semantically into your small languages. When should I go from the lazy form to the compressed form that give me a value? And you could actually have multiple such compression points. Okay? So we have one there. Okay. Oh yeah, and I did this ugly stuff. Oh yeah. So, anyway, you could actually have this one. So what do I do there? I'm turning my terminal float into a natural float. So somewhere, I need to have an operator that say, okay, I'm taking an expression and I'm converting it to some value. Okay. So, and that's what I actually did there. It's a bit different. I put it into the base expr. And I gave the base expr an operator of conversion to some types, which is value type. Okay. We will see how we compute value type afterwards. And what does it do? It computes the value of the expression. So I would just call function call operator on my current expression. Yes, that's ugly, yeah. Sorry for that. But the value type, come on, it depends. It depends on what? On whatever is stored into the base expression. If I have a terminal of int, I should return an int. If I have a float, I should be convertible to float. And if I have an operation that takes whatever and return a complex of double, I should be returning this. But the base expr class doesn't have any way to know which one is it, except by asking is derived class. So we use this quite ugly line 9. I'm not sure there is something more elegant. I'm taking opinion afterwards. What I do is, okay, let's try to build a fake derived and call its operator parents on it and give me the type of that. Okay? And that's probably the type of what it should be returning anyway. Okay, because by going down all the operator function calls, it will finally end up into a place where, oh, okay, that's a float. Okay. I tried to write something like operator decal type blah blah blah. Doesn't bode well. So that's the simplest thing I found about. I think that a better elegant way should be to have a value type meta function externally stored out of all the expression types and just call it whenever I need, okay? Just to doesn't have all this crooked stuff. But yeah, we can actually say, okay, conversion operator is also a compression point. That's another great classic, okay? And of course, I just call that terminal. You could actually call it variable, value, matrices, whatever, okay? But that just works, okay? And now, does it compile actually? Should be. Oh, come on. No, oh, no, this one does not compile. Okay, true. Doesn't work. Why it doesn't work? Forget that. Doesn't work. Why it's not working? Do I have all my information about derived when I compile base expert of derived if I add this using inside? No, because if I'm building a base expert of derived, that means I'm building a derived. And I cannot ask what's the frigging type of operator's parents on derived is, because I still doesn't know. My type is not complete yet. Okay? This works because it doesn't need derived to be complete when you try to take a reference to it. So that doesn't work. Okay? So if you want to make this work, actually, I forgot about this. Can you get my cursor back? Thanks. Okay. You probably want to have something like this. I'm not even sure it will work. So you probably want something like template, blah, blah, blah. And you want this. You probably want something like this, okay? And what you want to be, let's say value off, okay? And what you probably want to do is something like that. But do we really think it will be working? We can actually pass this, I guess. That won't work either.
Because when you install the base expert,
Yeah.
you will try to
Yeah. Yeah. We will still trying to instantiate something we should not be doing. And the one way to make it work, I think I have it into the other solution, but it's a bit more complex. You have to ditch auto and whatever. The only way to make it work is to delay the evaluation of these types by using the old school result of protocol that needs to be called whenever it has all the information. Okay. So, well, beware of this. That's one of the limitations of the CRTP. You cannot do anything in the base class that requires information about the complete type of the derived class. So, okay, forget about that. Just take this somewhere else, and let's just put it into, where should I be putting it? Yeah, terminal. But putting it in terminal is not very useful, okay, because we know its value, okay? Just that. Done. But what should be cool is to be able to call these conversion operators on, let's say, float of a plus b, okay? And like they say, when you end up with something complicated, this is left as an exercise for the reader, okay? So try to do this at home. You will see it's not that crooked, but you have to think about it a bit differently. That should be working. Yep. And of course, when you have that, you can actually, well, can I actually put it somewhere there? Yeah, actually, well, I cannot because I doesn't know the type, the return type, same problem, okay? So we wish we could actually do something like this, but it's not possible, okay? So that's one of the limitations of the systems, okay? You are bound to just ask for information about the non-complete type of your derived class. Okay. But you can actually live with this. So this notion of compression points is very important because that's where the magic happens, okay? You want your user to not know about your evaluation strategies. Just write something, and somewhere I would just go from the lazy representation of the tree to something that makes sense, sort of. Okay? I think that's the same thing. Don't think anything else. So that's where we go. So as we saw, that's the operator definition. We just put some tag with an operator. We just return the whatever, build a binary expression with a plus and whatever. So what is missing from this? What if I want to write something like some terminal plus some literal, like u plus 3? 3 is clearly not something which is a base expert. Well, don't have much choice. You will have to write the two others overload of plus, one taking random types and base expert on the left, or base expert and random type on the right. Okay. So that's 3 operator for binary operation, which means that if you add ternary operations, that's probably 7, yes, 7, and so on and so on. 2 power of number of arguments minus 1, okay? Well, should I do something special for unary expression? No. Why? Because the only stuff that interests me in unary expression is my unary function or operators called on one base expert. So you just have one to write for unary expression. So we wrote operators. You can actually write a function like sinus, cosinus, arctangent, copy, whatever you want. And the system is still the same. You wrote the function, take some arguments, put it into the correct box, and ship the box. Okay? And you should have somewhere into the box description what should happen when I'm coming down this special tree. Oh, what? Perfect timing. So, just finish on that before some question on this part, and then a small break. Yep. Other limitation is, currently if we do that, what if I want to take the exact same code and write something that just say, hey, by the way, what I want to do is, when I call toString, I get a string containing the exact string representation of the tree you just wrote. Well, you will take your stuff, you know, and your working shoes, and go down every damn base expression stuff and add the toString operations that do the whatever you need and so on and so on. And then Bob from the other departments come and say to you, oh, but now what I need to do is actually something that say, I'm taking this expression of operation on variables, and I want you to compute the derivative of this function. And then again, you write the stuff, you write everything back into the base expert. Problem is, if you just do it this way, it's fine as long as you have one stuff to evaluate. As soon as you have multiple evaluation schemes for the same tree, this system is actually a bit brittle and at least not solid with big S. It means that you don't really want to touch the code of the expression structure whenever you feel the need to write another tree traversal. That's basic 101. I mean, that's what the STL does. That's what you should be doing all the time. We need to find a way to separate the data structures that represent the tree from the tree traversals. Okay, so, well, we know how to do this. We can actually have a visit or an accept methods into somewhere, and we can just implement some kind of visitor patterns and probably solve everything. Okay, but take that in time. This very simple example is cool because we only do something, okay, one thing. As soon as you grow up and you need to do more things with the same tree, it starts to be a bit cumbersome, and you need to have something which is more, let's say, flexible on how you want to do this. And that's what we will be seeing, and that's how actually Boost.PROTO solves the issues by separating those two stuff. Okay, is there any question on this first part? Is everything clear now on what the expression template is supposed to do and how it works when you actually build it from the ground up? Any questions? So either I killed every one of you, or you all understood everything I said. I hope it's option 2. Any question? Yes?
I just want to make sure I'm kind of understanding maybe the way that you get runtime values back. It's because they're all inline, and they'll all be expanded inline until it gets the terminal done.
Oh, okay. So the question is, how do I get the runtime value correctly? So what happens there? So let's take the simplest example more than this one. Okay, let's take this one. And let's put it back. So what happens when I call eParents? I'm jumping into the eParents of whatever I got from this, which is probably the parents from binary expressions there. Yep. And what does binary expression function operator call does? It say, okay, guys, I will just call the same operators on my left and hand side. Okay. And whenever I got this evaluation done, I will just forward it to the function call from up. So I need to evaluate CA parents and CB parents to know what's going on. So what is CA and CB in our cases? That's D, which is a terminal. So I jump into the operator parents from terminals that just gives the value back. So CA gives me 4, CB gives me 4, and I will just call operators function call 4 on up, which happen to be a plus. which is, I don't remember where, there, and just do a plus. So it works just because we generate this chain of function calls. And yes, when you compile with all optimization, you get in line, actually, and you count on that for the performance, of course. But yeah, it's just that this recursive call will do whatever you want. You go down the tree up, so you get terminals, and you get back the value, okay? And speaking of inlining, this is a very important point. In this very simple example, if you look at this, I've been lazy by just storing every children by value because, okay, not complexing anything. Now, imagine that your terminal is not a single int, but it's a vector containing gigabytes of data, okay? You don't really want to copy it every time you build a new node into your tree. So one thing that people usually do when you do that, they store the sub-expression as const reference. Oh, sorry, as reference to const subtree. That's cool, but it implies something which is very, very, I'd say, I mean, when you say it, it's obvious, but people always miss it. If you store your sub-expression by reference, that means that the lifetime of your big expressions is basically limited by the statement it's built on. You doesn't want to store it into an auto variable because once it's gone, all you have is ending references to temporaries. You can cheat a bit by storing everything by reference to const and praise the gods that the lifetime extension kicks in, okay, but it's not safe. And it will bite you later because you will end up with a bug that something's blow up and you doesn't know where. And the debugging, when you build into debug, just works because the debug just do all the stuff one by one. But in release mode, it just blew up. So it's a very complicated issue. We will see that in Proto and we'll see that afterwards. You really want to store everything by value so it's safe, but sometimes it's not efficient. So we need to find a way to know how to take this decision, okay? But that's for the afterwards. Any other questions? Yes?
So far we haven't done anything that actually prevents temporaries or saves us on computation.
Sorry?
So far we haven't saved any computation or prevented any temporaries.
Oh, actually, we did. This example is actually very simple. We just store a single, a single integer, okay? Now, let's imagine what we store is vectors, okay? What will happen if you write your operator plus and operator times directly using vectors? You will end up with a code that say, let's build a temporary vector in which I will store the results, write a loop, fill the result, ship back the resulting vectors. And when you write d plus d plus d plus d plus d plus d, you will go there and you will get one temporary for every call to the plus operator. Compilers may see that something is crooked, remove some, but not all. And you will probably not get out of having all those memory allocation done. What happens there, if I put a vector of whatever inside there, I won't do anything to the plus. I just build this empty box, taking things containing reference to something else, okay? And then, when I evaluated the YOL expression, I will build a single temporary vector if needed, or I will probably just resize my destination vector and fill the blank with the evaluation, okay? So what we did, the fact that we doesn't do any temporaries is that when you look at plus, times, and other function operators, they don't do the computation. They just build this dangling tree of stuff that you get evaluated later. And when you evaluate it later, you can say, okay, there is probably multiple array into these things, but I don't care. I know that I will just resize myself and ask all of them, all of their value one by one, and you doesn't have any temporary vectors or whatever. That's what happens. I should have put that into the example, actually. We will see that a bit later, but yeah. So you save the temporary because you doesn't do any computation on the fly. You do a lazy evaluation of the tree, and you defer the evaluation later when you know that you have all your information and you can take conscious decision about how many memory you need to allocate. Okay, that's what's going on. Okay, and we make the assumption that the temporary expression objects are usually small and non-costly to copy. Yes.
Another question is, are we going to have a way to reach across maybe binary expressions?
Like, sorry.
Let's say you have a matrix vector.
Yep.
And you want to, like in compile time, you could use
Okay, so the question is, can we end up with a way to actually manipulate the tree so we can decide what part to evaluate first? That's basically this, okay, or all the decisions based on the tree. We will see that with Boost.PROTO. It's actually very complicated to write with this kind of system because it doesn't have any built-in introspection on the structure of the tree. You will probably have to write function and meta functions that will enumerate all the cases you may want and decide by calling the correct function. What we see with Proto is that basically you can say, okay, this is the kind of pattern that interests me, and whenever you meet that, do this. Okay? And with playing with this and some of the things that we will speak about later, you can actually order or split the way you want to make the evaluation work. But you need something more powerful than just a bunch of CRTP with simple classes. But yes, that's one of the motivations of Boost.PROTO. Okay, so let's have a break. And if you still want to hear about me, so come back in about 10 or 15 minutes.